Okay, today we have new announcements. Well, the old announcements are still there. Homework 1 is due tonight. Doesn't surprise. Lab sections are meeting this week. As you know. The programming assignment 1 is out. It's due September 27th. I encourage you to read it. Maybe take a look at it over the weekend for like 30 seconds, just so you know what it is. And then finally, I figured out how to put my videos on YouTube, and you know what? It wasn't that hard. Yeah, I know. You should clap, but no, you shouldn't, because it was so simple once you know how to do it. Anyway, so they're out. Today's plan is we're going to talk about insertion sort, and then we'll talk about memory models, and pointers, and pointer manipulation, and linear structures related to pointers. Any questions before we get going on things on my agenda? It's on your agenda. No? Okay. We just finished talking about selection sort last time, and this, for the sake of completeness, I've written down a proof. And so this is like a review of what we did last time, just to remind you about loop invariants and how to prove them. We had that loop invariant that says, in selection sort, at the start of iteration I, for all values of I, we have that the contents of 0 through I minus 1, not only are they sorted, but they're also the smallest things in the array. And in addition, the string hasn't changed, so we're not changing anything. And then we have a proof, which is pretty straightforward, but let's just look at one piece of this proof, maybe two pieces. The base case, for example. When I equals 0, what is this saying? It's saying that the contents of A0, let me write this down. So the base case is when I equals 0. That's before the first iteration of the loop, right? It's at before the I equals 0th iteration of the loop. And what our invariant is saying is that it's saying that A0 through I minus 1, which is negative 1, is the smallest strings in the array, and they're ordered. So, does this seem problematic to you? The point is that you have to interpret this indexing in the right way. This range from 0 to minus 1 is empty. So this is saying that the empty array has the smallest elements in the array, the smallest 0 elements in the array, which is true. And it's an order, which is also true because it's empty. So anyway, that's a little weird, but anyway, it's true. And then the other thing there's only two things we're going to talk about on this slide. The second thing is the other y. It's way down here, which means we have to read everything up to that point. But let's just sort of go quickly. That's in the inductive step. We want to show that it's true at iteration I plus 1. And that involves taking the fact that it was true at the start of iteration I, that is the inductive hypothesis, and then using the correctness of find min, that was the algorithm that sort of went through and found the minimum in the array, the remaining part of the array that we haven't seen yet, finding the minimum in that part, and then swapping AI with that minimum element. So it's putting the minimum element into location I. Okay, so when it does that, that is certainly true, because that's what find min's correctness tells you. It tells you find min will find the minimum in the array AI through AN minus 1. And we just swap that minimum into location AI, so we know that AI is the smallest out of all of the elements in that array, the remaining ones from I plus 1 onwards. The why is about this. Why is this true? Why is AI bigger than the first I minus 1 or the first I things if you count 0 as one of them? Why is AI bigger than those or greater than or equal to those? What fact are we using there to make that claim? This is like the whole, this is the whole deal. This is like why we're doing induction.
Because it says at the start of the iteration, A0 to AI minus 1 for the smallest strings in A.
Perfect. It's because of the inductive hypothesis. The inductive hypothesis says not only are A0 through AI minus 1 sorted, but they're also the smallest in the entire array. And so we know the next thing, which is AI, which is not part of that group, but is in the array A, will be larger. And so it's bigger than A0 through I minus 1. It gets plunked down in its correct sorted order because it's not only less than or equal to the elements in A from I plus 1 on through n minus 1, but it's also greater than or equal to the elements that preceded in the array. And so it's in sorted order, and now we know that we've established the loop invariant for the next step. Yes?
So why in this case are we doing like for all I up to n minus 1? And then the last time we did up to n.
I don't know. Maybe we should go up to n. That's probably a good idea. Maybe it's because I wrote these at like, the middle of the night last night and didn't do that. Why this? I think that's probably what we would like is to have it be true at n. Otherwise, it's not going to be true at the end of at the end of the execution of this for loop. Excellent. So that n minus 1 should be n. Yep.
Sorry, and then I didn't quite understand like what it means by like in the induction hypothesis, like at the start of iteration I plus n.
Oh. The question was, why is that there? The way you read that is that you're starting at, your invariant is true at the start of iteration I, and I is also less than n. That's what the assumption is. Why would I assume that I is less than n?
Is it because you're making the assumption that the loop invariant holds for all elements in the array from the first one all the way up to n minus 1. So then we can use that to prove that this works when we check the nth element.
Sort of. If I understood correctly, I mean, the real reason that we did this is because if I was actually equal to n, the loop wouldn't execute. And so we couldn't make any of the claims about the inductive step if I was equal to n. Because what would happen when I was equal to n is it would just fall out of the loop, and we wouldn't be able to say that we swap something with we swap AI with A min and all of this other stuff. But it's just not true, because I is too big. It's already big enough that it's triggered the failure of the loop and we fall out of the loop.
Right, but we still need it in the loop invariant. Right?
We don't need it in the loop invariant. we need n in the loop invariant, but we don't need the inductive hypothesis to hold for n, because we're only proving up to n. So we only need it to be true for some arbitrary value of I that's less than n, or less than or equal to n minus 1.
Yeah, so then that would show that it would hold up to the start.
That's right.
Okay.
Yeah, holds up until the start of it.
Okay.
Any other questions about this? Okay, excellent. We're done with selection sort. Now we have this mystery function. Another mystery function. This one looks an awful lot like the old one. So this is, we have an assumption that A0 through AI minus 1 are sorted, and then you pass in this value I, and it picks up the ith value in the array, call that value, or val, and then it starts a loop. But this loop is different than the loop for find min. This loop isn't incrementing j, it's decrementing j. So you see there's a while loop there, starts off with j equals I, and then it's checking while j is greater than 0 and some property is true. Then if that happens, it will copy the j minus 1th element into the jth element, and it will decrement j. So it's working backwards. It's going decreasing j. And I drew an example down at the bottom because it would save time and you could actually read it. This is sort of what you might do if you're trying to understand what this code does. It's what I did to make sure that I was doing the right thing. So these are the indices 0, 1, 2, 3 of the array. The initial values that are passed in are I equals 3. And because I equals 3, the code picks up this value and sets it to val. So val is equal to 15. Okay? And now what it does is it enters that loop with j equals 3, and it says, is a j minus 1, which is this guy, so that 30 is aj minus 1, and it checks to see if aj minus 1 is bigger than value. And in this case, it is. 30 is bigger than 15, and so what it does is it copies this j minus first value, it copies it over the top of 15. And so the new array is this one right here. Is it good? This seems a little weird because now we have two 30s in the array. That's okay. We keep going in the for loop, and it checks the next thing, which is this 20. J is now decremented down to 2, so it's going to check j minus 1, which is 20. A of j minus 1 is 20. It'll compare that against the value, which is 15, and it's still bigger. 20 is bigger than 15. And when that happens, it does the copy thing, so it copies 20 over the top of 30, and we now have this array, which is the third array that's shown here, where we have two copies of 20. Finally, when j is equal to 1, we look at j minus 1, it's 10. So the array location is 10. 10 is smaller than 15, and so the test in that while loop, aj minus 1 greater than val, fails. And the thing just falls out of the loop. And when it falls out of the loop, it sets aj, which in this case is j is 1. It sets this value here, this 20. It changes it into 15, the original val. Okay, so what is this doing? Do you ever play bridge? Card game? No? Nobody ever plays bridge. Do you play any card games where you have to sort the hand of cards in your hand? Now you pick up the new card that you get and you go, da-dum, 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 da-dum. That's where it goes. So you pick up the next card, and you look in the current hand of cards that you have. Do you even know what cards are? It's like, no, you must know. Anyway. You pick it up, and you march it down, and you plunk it into the place. So you're picking up the next one, and you're putting it into the right location. And then you go and you pick up the next one, and you put it, yeah.
Oh, but this is assuming that I is placed in somewhere like very far out to the right, right? Because like for example, J starts at I, but like what if I is already like a very small number? Like what if I was like 0 or something? Because like what this function is doing is like you get an I, and then assuming that J, like I is somewhere smaller than somewhere like to the left, then you have J, and then you decrement J.
Oh, okay, but be careful, because I is an index, and the things that are being compared are the values in those index locations.
Right.
So if I is small, then that means that you're only interested in the very first part of the array. So if the index I is like 0, then, well, frankly, it's never going to be called on 0. But if it's 0, then there's a problem. Maybe I should write that down. Is that what you're worried about when I is 0?
Yeah, or just like a very small number when, like for example, if the value of I should be somewhere like very, which belongs to like to the very left of the array, when it's like very far out, right?
Again, it's not the value of I, it's the location, the value that's in the location at index I.
Right.
So, but you're right about the fact that I should be bigger than 0. Otherwise, well, if I is equal to 0, what's going to happen? Nothing. So it's okay. It just means that nothing happens. But if I is 1, then it'll still work. And if the location, if for example, if we were in this situation and instead of having 15 in the ith location, we had something like 0 or -3, something really small, what would happen? It would march all the way back down to the beginning, to the index 0, essentially shifting everything forward by 1, and then it would plunk the value into location 0. So I don't think it's bad. I think,
Right, yeah, because it assumes that the array is already sorted.
yeah, it assumes that A0 through AI-1 is sorted.
Oh, okay, thanks, that makes sense.
Any other questions about this? Plunk. Plunk. If I had more fingers, I could add another finger. And then there's 2 fingers. Like that. Okay. And it always is inserting into the correct position. What would you like to call this function? I know what I called it, but you can look on the next slide and see what I called it. But you want to call it something else? What's that?
Insertion?
No, this is not insertion sort. This is, what?
Just insertion.
It's just insertion.
Find where I belong.
Find where I belong. Where do I belong? That's a good one. I have a more prosaic one. It's not as nice as that one. Where do I belong? Yeah.
Can you explain why I needs to be
Greater
greater than 0?
than or equal to 0.
Yeah, why? If it's all sorted, why does it have to be like greater than 0?
Oh, the only reason was because I was worried about it being negative. But what would happen if we put in a negative value for I? Well, we would get an error, because if you try to access an array location at -1, bad things will happen. But that's all. And then it just will be an error. But the reason that I put that up there was because I misinterpreted the question as being something about the value of I being too small. But it wasn't a question about the value of I being too small. It was a question about the assumption that it was already sorted up until I.
Yeah, I understand.
Yeah. Yes.
Also, what this function is doing is that it's trying to shift all the numbers larger than down to the right.
Yes, it's trying to make a spot for it. So it's like when you come into your hand and you got your new card, it's going scooch over, okay, you scooch over, move over, move over. Okay, that's where you go. It's going to make space for the place where it's going to put the new card.
Also, the function gets called make space
Make space.
for balance.
Make space. I'm going to stick with mine because I wrote it on the next slide. But I like all of these. In fact, I like where do I belong? That's a really deep thing for computer science. But I called it, what do I call it? Oh, I called it put in place. That's just terrible. Put in place. Where do I belong? Okay. Where do I Okay, everybody good? This is a subroutine that's going to be used in a sorting routine. And so one would like to prove something about this. It's got a loop. It's trying to maintain some state as I stick cards into my hand. There's a property that the configuration of the array has at every step of the loop. I want to maintain that property, but I have to capture that property in a loop invariant. You get to think about that. What is the loop invariant? And because I'm interpreting the sort of silent dread in the room correctly, we will skip this proof. Because there's just sometimes too many loop invariant proofs. But this is crying out for a loop invariant proof, and it's a great way to practice your skills at designing loop invariants and proving them by induction. This is not so difficult to do, not a bad proof. In fact, we should do it, but we don't have time. Okay? Yes?
Wait, is the loop invariant just that j has to be greater than 0?
No.
Oh no.
No. J greater than 0 is not a loop invariant. I mean, it is a loop invariant. I beg your pardon. It's a loop invariant, but it won't help very much. Anyway, think about it. Yeah.
So what's the runtime of this?
Oh, that's a good question. Now I put that question down at the bottom. Ah, good for you. What is the runtime? That's that annoying thing that people do. You ask them a question, you expect an answer, and they ask it back at you. What is the runtime?
It would be O n, and n would be linked with a. But if it's already sorted, then it's probably missing one.
Wait. She said it's order n if n is the size of the array. So let's just say the size of the array is equal to n. And then there was some other words that I didn't pay any attention to, but there was something that was sort of like if it's already sorted, then it's constant?
Yeah, in the best case, it would just be constant.
In the best case, okay, all right, but okay, you're being an optimist. That's perfectly good. I'm very happy for you. That's great. But we're all pessimists here. No. Is everybody happy with runtime of order n? This is the worst case runtime over inputs of size n. And it's true. It's order n. However, it also is order I. If you allow I to be a parameter in your running time analysis, And the running time of this code is also order I, because it never takes more steps than basically I. If I ask you to find, if I had 3 cards in my hand and I asked you to place the 4th card, it doesn't care how many cards there are anymore. It's just going basically 3 operations. So the other thing you could write down is order I. What did I write down? Oh yeah, I wrote down. Both of these are worst case over inputs of size n, but one of them is also worst case over values of I. So this one here, we've also assumed that I can be as large as n, which it could be. So this is also worst case over I. Oops. Which you might say, since I is part of the input, when you say worst case over inputs of size n, why don't I just assume that I is n because it's worst case over all inputs of size n? You might say that, and then I might say to you, well, because if I know what I is and I pass it in as a value, and I want to know how long the running time is, I might want to know that running time as a function of I, not as a function of n. I might not want worst case over all inputs of size n. I want worst case over inputs of size n for a particular value I. So both of these are worst case over inputs of size n, but this is for a particular I. A particular I. As you will see, this is maybe useful. Yeah.
Just for confirmation, so for the parameter I, is that defined to be the number of elements that we're checking plus the one that we're trying to insert?
No, it's just a parameter to the function. You could pass it in as whatever you'd like. As long as it's bigger than 0 and less than n, or greater than or equal to 0 and less than n, you're okay. So whatever it is, that's the value. Now you can interpret it as you wish. You've given an interpretation to it. Okay, that seems like a reasonable interpretation. But that's not what it's defined to be. It's just the parameter that comes into the function. So no matter what that parameter is, and no matter who cooked it up, some crazy person who called your function with some weird I, the running time is order I. Yeah.
Can we say in this case the running time is like theta?
Can we say it's theta of I? What do you think? In the worst case?
Yeah.
Worst case theta I. Yeah, I believe that.
Well, so isn't it always like if you say it's like in the worst case it's like O of n, but can't you always say it's like in the worst case it's theta of n?
Can't you always say if I say in the worst case it's big O of n, then in the worst case it's theta of n? If I tell you that in the worst case it's big O of n, that just means that there's a constant such that the running time is less than a constant times n.
Yeah.
Okay, so I'll give you the following code. It says return. That code has a worst case running time of big O of n. However, it does not have a worst case running time of big omega of n. It has a worst case running time of big omega of 1. And so a tight bound on its running time is theta of 1.
Okay, but if we have like an explicit formula for like the worst case running time.
I did. And you mean it was tight before? You telling me that it's tight and you're asking is it tight?
I mean like so if you have like an explicit formula for like the worst case running time, and then you can just say it's like theta whatever that formula is.
Okay, so there's two things going on. There's the analysis of the runtime in the worst case. And then there's a question of how asymptotically tight that analysis is. if you have an exact function for the number of steps that the algorithm takes on an input of size n or whatever, you have an exact function, then coming up with a bound on that function which is tight is a second step. So, for example, in my stupid return function, there's a running time of 1. 1 is a function which is big O of n. It's also big O of n squared. It's also big O of 2 to the n. So the step that I'm worried about in what you just said is your asymptotic analysis of this running time. You have the running time, you analyze it asymptotically, and the asymptotics that you get are not tight. Then you wouldn't have the ability to say that just because it's big O of n means it's theta of n.
Okay, yeah. But like if it's just 1, then you can just immediately say it's like theta of 1. 'Cause that's like,
Yes. If it's 1, then you can immediately say it's theta of 1.
or if it's, because like in the last example, you said like in the worst case is like n times like n minus 1 over 2.
Yeah?
And then you can just immediately say that's like theta of n squared.
Yes. I can. If I ask you on an exam, though, and I say something like prove it, then you can't.
Then you have to.
You have to do something.
But
But maybe this raises another question, which we have. Okay, I'm going to tell you this because it's important. It is not true that if I give you a function, you can always find a tight upper bound and a tight lower bound on that function. Like you could have the function if this works, it'll be a miracle. Wow. You could have something like, not that. And you guys are laughing. They're in the back, they don't know what's going on. I'll write it up here. That's why I have this. So if I write n to the 1 plus sine of n, that's my function. That function you cannot get a tight bound on. It doesn't have a theta bound because sometimes that function is n squared. And sometimes that function is a constant. So it oscillates as n gets larger. And there's no one function that will bound it from above and bound it from below. Okay? All right. Fortunately, these don't show up very much in running times. Because typically running times only increase with size. Okay. We're good? Great. Insertion sort. Insertion sort uses the thing that we just, the card thing. It uses that to sort. And it does it exactly like you would expect. It starts off assuming that one card only is already sorted, and then you pick up another card and you put it in place. And then now you've got 2 cards that are in sorted order, and then you pick up another card and you put it in place, and you've got 3 cards. What's a loop invariant? Quick, we don't have any time. Loop invariant. There's a loop here, it's got an invariant. What is the invariant? A bracket 0 through I minus 1 is sorted. Yay! Great. And by sorted here I mean non-decreasing order. Loop invariant. Great. So now we have a loop invariant. Now we prove the loop invariant in about 3 minutes. So in the base case, when I equals 1, that's the start of the 1th iteration. A 0 through 0, which is A 0 through I minus 1. By the way, here's the loop invariant right up here. A0 through 0 has only one element, so it's always in sorted order, so we're done. Check. Happy? Unhappy? Step 2, induction hypothesis. Assume it's true at the start of iteration I. The loop invariant, that is. Inductive step. Since it's true, by the inductive hypothesis, at the start of iteration I, and put in place changes A so that A0 through I is sorted by the properties of the put in place algorithm, then the invariant holds at the start of the next iteration, which is I equals I plus 1. What's different between this and selection sort? What's generally the difference between insertion sort and selection sort? Yeah.
You don't need the other invariant.
I don't need the other invariant.
That was the second top of the list.
It's not that I don't need it, I don't have it. So I'm not able to claim that my first I elements are the smallest I elements. All that I can claim is that the first I elements are in sorted order. And the power of selection sort was that it was able to take advantage of that, because all it had to do was select from the remaining ones the minimum, and then it knew where to put it. But that's also the danger of selection sort, because it has to select from what remains, the smallest one, in order to put it in the next spot. Whereas with insertion sort, it knows only that the first I elements are sorted, or I minus 1 or whatever it is, and then it picks up the next card, and it marches along until it plops it in place. Now it has more things sorted, but the minimum may be still to come. It might still be out here. It's not that these are the smallest things, it's that they are just in sorted order. But that's enough. If this loop invariant holds, it's enough to sort the entire array, because at the end, the entire thing will be sorted. Which one of these two algorithms do you think is faster? You know that they're both... Oh yeah, we haven't done running time. What's the running time of this thing? How much does this time run? It takes order I, or if you'd like, order n. And then you sum this all up of 1 equal to n, and you get the sum of I from I equals 1 to n, or maybe n minus 1. And that's n times n minus 1 over 2, or something like that. And so it is how much? Well, that's a function we know is theta of n squared. So it's theta of n squared. If you think back, selection sort was also theta of n squared. Neither one of them is faster than the other asymptotically. Right. So why do people use insertion sort over selection sort? When would you use insertion sort instead of selection sort?
When you're using insertion sort, you already know that the list is sorted, so you only have to compare it to one element at a time, compared to selection sort, where the remainder of the list is not sorted at all. So every time you go through a loop, you have to check for the minimum and bring it to the front again, which is going to be more accurate, I suppose.
So you think that insertion sort will run faster on arrays that are
Shorter.
shorter?
I mean,
You mean
that are mixed up.
insertion sort will run faster on things that are mixed up? Is that what you're saying? I'm just trying to get clear.
Isn't insertion sort where the list is already sorted and you're only putting it one?
But insertion sort is like the card game. You pick up the next card. So it's assuming that the first part is sorted, and then it picks up the next card and puts it in place. Now, I think what you're saying is that if the next card that I picked up was bigger than all of these cards, how much work do I have to do? 1. Pick up the next card, and if it's bigger than all of these, 1. So I pick up the next, you got it? 1. So what arrays are going to be really fast for insertion sort? Already sorted ones. If they're already sorted, boom, it's really fast. What a stupid thing to do is to call a sorting routine on something that's already sorted. That's what you're thinking. That's where you're wrong. Think about what people do. You have your list of friends in your, I don't know what you have on your phone. You've got this list of people, right? That list is increasing by friends very rapidly because you're now back at school and you're adding friends to it. But you're adding like maybe 12 a day, maybe 28, I don't know. You know, that's minuscule compared to the total number of people, total number of friends. Most of that array has already been sorted in your phone. All it has to do is insert the new ones. And that's very fast for insertion sort. So once you, at the end of the day, when you're sleeping and your phone's working, it's running insertion sort to reorder all your friends. Because there's only been a small change. Most of the array is still sorted. Let's see this work. Oh, this is the correctness stuff. Never mind. We'll look at that in a second. This is a great place to go to. This is, can you read that? toptal.com, toptal.com, developers sorting algorithms. It's implemented lots of sorting algorithms, including selection sort and insertion sort. Those happen to be the first two columns. Insertion sort is the first column. Selection sort is the second column. And what we have here is different inputs for those algorithms. Nearly sorted, the top one is random, the next one is nearly sorted, the next one is reverse sorted, and the bottom is a few unique values spread around. Got it? I'm going to push play. Before I push play, I would like you to tell me who is going to win between insertion sort and selection sort on each of these types of inputs. So, random, you can vote for insertion sort or selection sort. Nearly sorted, insertion sort or selection sort. The other ones, we're not going to worry about those. We are going to worry about them later, but right now we just know those first two. How many people on random? Who's going to win? Insertion sort? Selection sort? Tie? We'll see. Nearly sorted. Insertion sort? Selection sort? Apathetic? Reverse. Insertion sort? Reverse sort. So like the things are coming in the wrong order. Biggest to smallest. Insertion sort? Selection sort? Isn't this fun? And then a few unique, we'll see what happens. Okay, ready? Here we go. Everybody watch so you know which one wins. Whoa, insertion sort's done with nearly sorted. Wow. I didn't expect that from the first row. Did you? Can we do this again? Yeah, you know what's happening for random? Why do you think it's faster for insertion sort? Who, what, where?
Is the first column insertion or selection?
First column is insertion.
Okay, first column. I just didn't see it.
No, I'm just checking your eyes. Oh, come on. All right. It's a little blurry, I agree. But it's not my website. So granted, they weren't expecting to project it onto a school, which I don't think. But do you know why in random insertion sort was faster? If it's random, how many comparisons does insertion sort have to make when it picks up a new card? It's random. It's a random order of the inputs. So how many comparisons would it have to make, probably? About n over 2, right? Well, half of the ones that are there. About half of the ones that are here, so I over 2, I guess. That's how many it has to do. How much does selection sort have to do? it has to go all the way to the end of each time it has to do n and n minus 1, or n minus 1 and n minus 2 and n minus 3 and n minus 4. It always has to do that. So when insertion sort is run on a random, it's basically saving by a factor of 2 over what selection sort has to do. Let's do it again. It's even better than select. It's even better on reversed. That's weird. I definitely would have voted for selection sort being worse on reversed. Other one. I mean, insertion sort being worse on reversed. But anyway, now you get to see, by the way, now you can look at all the little pictures. Look at all the little pictures and sort of see what's going on. Some of them are really fast. Shell sort. Poor bubble sort. Okay. Anyway, we'll learn about these sorts, the other sorts, some of the recursive ones like merge sort, heap sort. We'll do, we won't do shell sort, but we will do merge, heap, and quick. We'll talk about them in this class, but we won't talk about them right now. We might not talk about quick sort, but we probably will. Okay. Everybody happy? At least now you sort of understand there's running times that are worst case the same and squared, but for particular inputs, one is better than the other. And in particular, insertion sort is often used because it assumes that there's a incremental addition to an already sorted list. Okay. How many people are taking 213? Okay, that's good. How many people are not taking 213? Okay, that's good too. Wow, okay, it's about right. All right, so I beg your pardon if you've already seen this in 213, but if you haven't seen it, it's good to see it, and if you have seen it, it's good to see it again. The way your computer works is there's some central processing unit, and occasionally it needs to perform an operation on data that's stored in memory. And it provides address to the memory unit. The memory unit looks in its memory, and the address is just an index into a big array, which is the memory. So it starts at address 0, and then it keeps incrementing. And for whatever reason, it's because it's more succinct, they express addresses in hexadecimal notation. So that means that you see things like A's and B's and C's and D's and E's and F's. In the hexadecimal means base 16. So you get these weird numbers for addresses, but they're just indices into this array. And inside of the array, the memory, at a particular address, is something that fits in a word of memory. In this case, I've written down numbers, like 42. And so when you put in the address 7, it looks up under array address 7 and returns 42 on the data. That's the data bus. There's the address bus, the data bus. Got it? That's the way your memory works. Okay, that's a read. There's a similar thing that works for writes. With a write, you send both address and data, and the data gets copied into the array, the memory array, at the location, at the address that's been given. That's it, except for all kinds of bells and whistles. That's the memory model inside of your CPU. And those bells and whistles are somewhat important, but they're not terribly important for understanding pointers, which is the thing we're going to understand next, and what you're going to need for your programming assignment. So we'll talk about pointers and pointer manipulation on Monday.